Hey everyone, Mr. Cummings here, and welcome to this video on deriving the conservation of momentum equation. So we're going to start this derivation by just looking at an example scenario. So let's say we have two carts that are on a collision course with each other. And so cart A is traveling to the right, cart B is traveling to the left. When these two objects collide, they're going to exert forces on each other. So the force versus time graph that we see plotted down here, or just sketched down here, the force that cart A exerts on cart B is going to be this positive force here. And that's because cart A is going to push cart B to the right, which is in our positive direction. So the blue graph here is going to be the graph for the force delivered to cart B. And then the red graph here is going to be the force on cart A from cart B. So we can see that this is negative because cart B is going to be pushing it to the left. And we can see that these two graphs are mirrors of each other, so they're reflected over this x-axis. And if we remember from our previous learning, the areas under these graphs are going to give us the impulse on each object. So the area under the blue graph is the impulse on cart B, and the area on the red graph, under the red graph, is the impulse on cart A. So diving in a little bit deeper to this graph, we know that the forces everywhere on both of these graphs are going to be equal, but opposite in direction. So equal in magnitude, opposite in direction. That's Newton's third law. They always exert equal forces on each other. The two force graphs occur over the same time duration, and that's because for the time that A is in contact with B, B is in contact with A. So the collision for both of them takes the same amount of time, which makes sense. And then what we can conclude from both of those statements, and also from looking at the graph, is that the impulse or the change in momentum for each cart is going to be equal in magnitude but opposite in direction, which is where this negative sign comes in here. It's not saying the impulse on B is negative, actually the impulse on A is negative. It's just saying the impulse of A is the opposite of impulse B. And we see that the change in momentum, which is the impulse, has that same rule here. So this is going to be pretty powerful in our derivation of the conservation of momentum. And this is actually what's going to lead to this derivation. So since we have the forces on each object are going to be equal and opposite, and the time of the collision is the same, the product of the force multiplied by the time is going to be equal and opposite as well. This is basically just saying that the impulse of object A is going to be equal to the impulse of object B, which is the same as saying the change in momentum of object A is going to equal negative the change in momentum of object B. Now, knowing that a change in momentum is just the final momentum of that object minus the initial momentum of that object, we can rewrite this above expression as the final momentum of object B minus the initial momentum of object B equals negative the final momentum of object A minus the initial momentum of object A. We can then distribute the negative sign on the right-hand side, changing that right-hand side to negative the final momentum of object A plus the initial momentum of object A. So the next step here is to rearrange the equation so that we're grouping initial terms and final terms on the same sides of the equation. Then using the equation for momentum, P equals mv, we can substitute in m and v for each momentum term in this equation. So what we get when we substitute this into our equation is the mass of object A times its final velocity plus the mass of object B times its final velocity will equal the mass of object A times its initial velocity plus the mass of object B times its initial velocity. So it doesn't really matter which way we write this equation, but because we read left to right, we're actually going to put the initial terms on the left-hand side and the final terms on the right-hand side. So we're just switching this around. And what this leads us to is the sum of the initial momenta equals the sum of the final momenta. In essence, we're saying the total momentum of the system is constant and it is conserved in this collision. And so now to complete the steps here, we're just going to write in all of the different steps that we did and explain what we're doing in each step. So the conservation of momentum equation states that the total initial momentum of the system is going to equal the total final momentum of the system. So this equation is true as long as the external net force on the system is equal to 0. So if we have two objects that are going to be colliding or interacting with each other, then we can expand this equation for the momentum of each object initial and the momentum of each object final on the left and right hand sides of the equation. And then using the equation momentum equals mv for each term, we can write the conservation of momentum as the equation ma times va initial plus mb times vb initial equals ma times va final plus mb times vb final, where a and b are just objects a and b respectively. And that's it on this video on deriving the conservation of momentum equation. Thanks for tuning in, and I'll see you next time.